Good morning, dear students. As we know, and we entered into the second unit. Yesterday, we have seen the first topic by name Elements of Visual Interpretation. See here, in the previous case, the previous topic, we have seen how the images will be analyzed. And in the previous cases, when you have a look over there, in the past what we discussed, the first unit syllabus, we discussed and you are very well content about the introduction of remote sensing, what we have completed in the first unit. See here, when coming to the second unit, we will discuss the first topic, how the analyst is going to interpret the characteristics of an image. For that, and we discuss, there are two techniques. Number one is visual image interpretation technique, or else techniques, and the other one is digital image processing. We have seen what are the different elements that lies in visual image interpretation. And hope you all know how the process of remote sensing the way it get initiate, the way sensor gets the target image through the scanning or else the receiving of electromagnetic radiation. The same has to be sent to the processing station. That means you know what is EMR and you know how the image of the target is being recorded by the sensors. After recording, it is reaching to processing stations where we need to analyze the characteristics of the image. That means nothing but target. For that, we discuss image elements or else visual interpretation elements. The first and foremost thing we have seen size. Based on the size, the images of spatial data can be analyzed. Shape, shadow, tone, texture, and then pattern, association, sight. All these we discussed yesterday in the previous class in a more elaborated manner. Now, after visual image interpretation, in the previous class itself, we entered into the second step of image analysis, or a second category of image analysis, that is nothing but digital image processing. See here, digital image processing. In the previous case, we have seen elements, visual interpretation. I didn't mention any connected word here. There are three words: elements, visual, and interpretation. The same way we used to discuss in classrooms. By visualizing the elements, what are those elements? These are the elements: size, shape, shadow, tone, texture, pattern, association, all, of course, sight, all the elements. For what? To interpret the spatial data. See here, the same way, here also there are three words: digital image processing. Digital camera, you might have seen. In the digital mode, you can enhance the features of the target. You know, you never approach, you can enhance and you can manipulate the images. In the image, you have seen a person. If you try to see the same person in realistic conditions, there is no surprise. Even if you ask the same person, where is he or she, by showing the pic what you have in a digital mode. That means what I am speaking is here. You all know that the images of the people, they want to keep as a reference. They used to enhance the contrast and brightness of the faces and the features what they want to highlight. What I'm speaking is here, the processing that is applying to the digital images in order to get the best out of the pic is we can call as in a processing method. See here, digital image processing. See here, you know, when the EMR reach to the process station with a number of, you got then a spatial data. By seeing and by applying those elements, you are able to, what we discuss in the name of visual key elements of visual interpretation, you can interpret the information of the image. Now here, before you are applying anything to the digital images, you need to make those images in such a way they can fit for processing. That means before processing, the techniques what we are applying to make those images fit for the processing called as image pre-processing. You may be here quarterly examinations. I think pre-quarterly may not be there. Maybe certain institutions may have, and if they may call even pre-quarterly. Pre-final exams we used to hear most familiar. That means here pre-final examinations objective is to make the people, to make the students get ready to face the final examinations. Here pre-processing in the sense, the images are processing, as the images are getting ready to face the next step by name processing. In the pre-processing method, what we are doing, what are the different techniques that can be employed, that can be adopted to make these images fit for processing. Now, what is the pre-processing technology and why we are doing all these things, we will discuss now. The whole process of pre-processing of digital images can be categorized into two steps. One is correction of radiometric errors and correction of geometric errors. Yeah, the question is, what is radiometric error? What is radiometric correction? If the flaws are occurred how the why what how these flaws may happen or happening as the EMR is traveling through the atmosphere somewhere other way. There most of the cases there is a possibility of flaws which we need to correct them. If those flaws are, if those mistakes are because of the incorrect calibration of the detectors or incorrect function of detectors or sensors, they are comes under radiometric errors. And these radiometric errors, or as the correction of radiometric errors, includes the following techniques. The first one is replacing missing scan lines or else removal of missing scan line. See, missing scan line. See, in an image, see here only. This is the digital image of one particular object. We learned in first unit itself. The images are recording with respect to the resolution that are assigned within a brightness value of 0 to 255 called as digital number. And if it is the image of one particular target, sometimes because of the non-functioning of detectors, one line brightness values may miss. In such cases, the function is replacing of missing scan lines. That means the missing scan line is replacing with what? And how you can replace the how we can replace the missed scan line? Simply by adding the digital number of pixel, respective pixels, after adding the primary line pixel values and the subsequent line pixel values to the missed line, whatever the answer we got, that must be averaged. That means by 2. By 2, whatever the value we got, that will be depicted here. That means 170 plus 221 by 2, whatever number you got, you are going to depict here. If you got any any point numbers, 145.5, in such cases, try to make the round off. Try to round off the number. This is what about removal of missed scan line we discuss. If two lines are missed, in this way you need to write in your examination. Simply see here 146 I mentioned here. See, some 170 by 119 by 2, whatever the value you got, if it is in decimals, in points, that number has to be depicted here. In the same way, if two lines are missed, the first line values are this is the first line and it is the second line. The first line values are repeated with the previous line values. Once we got the first line values by replacing the previous line values, the process is seen. Simply by adding and averaging whatever the value u and v got, that will be depicted in the second missed line. If three lines are missed, the first line values are repeated with the previous line values, and the last line values or third line values are repeated with the subsequent line values, and the middle line values are by adding the first line and third line values with averaging whatever the value we got, that will be in the middle, that is in the second line. This is what about if 3 lines are missed. If more than 3 lines are missed, there is no way the process has to be done one more time. Because why we are repeating the values of the previous line here? Because in most of the instances, the features on the ground surface may hold the similar characteristic features. That is the reason we are depicting the same values in the missed scan line if more than one is missed. If two are missed, for first line is replacing the primary values, and the second line is by adding and averaging. Third line, 3 lines are missed. The first line, the primary line, whereas the previous line values are replaced with the first line values are replaced with the previous line. The last line, that means third line values are replaced with the subsequent line. The middle line values are simply by adding the first line and second line values, what we got, and simply with averaging the value, whatever we got, that will be in the center line or third line. More than 3 lines are missed. The process has to be done one more time. See here, stripping. Here, the process is, we named it as destripping, stripping, destripping, activation, deactivation. You know the meaning. Active and deactive, stripping and destripping. Now, what is the meaning of stripping here? In the previous case, we have seen there is no values here. There is no values. That means the entire line has missed. But in the stripping, in the sense, the lines are missed, but the lines are missed, but the values are abnormal. See, that's what you wrote. We wrote, these are not constant data values. These are pattern of lines having low or high digital numbers. In the previous case, entire line values are missed. But here, stripping in the sense, the values are there, but they are either high digital number values or as low values, which are not matched with the surrounding line values. That means, imagine an image of your friend or else somebody. The face brightness is similar except at nose. All the brightness values are equal except one particular part. If the particular part digital number values are high, and if they are not matched to the other features of the face, the particular part looks like an abnormal. See here, all the lines are having somewhere other way nearby equal values, but in that particular line, either it have low values or digital high values. The process where removing those lines are called as destripping. Stripping in the sense, having digital numbers high and low when compared with the nearby surrounding pixels, entire line, I'm speaking about entire line values are not matched, high and low values. In such instances, the line will be removed, or else the process of removing those strips, not lines. If line is missed, entire the feature may be missed. What we are removing of those unbalanced digital number values. If you are removing those digital numbers, that means you must keep any one of the number, which number and how you can depict the numbers, because there is no possibility of removing entire line. But what we are doing, we are removing a stripping. Stripping means high and low values in the pixels. The stripping has to be removed. How we can remove? Simply here, the correction of radiometric matches can be done by adopting one sensor and adjusting brightness of all pixels. That means one reference image will be taken which belongs to the same target, what we have as in a file copy. By comparing the digital numbers at that particular point, the numbers will be replaced. That is one number. That means those low and high digital number values are replacing with the other values what we have an image of the similar object, the same object as in a copy, that is called as distributing. The other way is by adopting Fourier transformation. What is Fourier transformation? This is not in your syllabus, but we are going to discuss in the days to come in our coming classes. Keep in mind, the Fourier analysis is not in your syllabus. It's a big topic and we are not going to discuss, but we are going to discuss what is Fourier analysis in the lab as far as the curriculum. Simply by comparing the reference copy of digital numbers, those abnormal, those low and high digital number values will be replaced in the process of districting. The third one is random noise. Now, what is noise? See here, random noise removal. Before we are going to discuss random noise, you must know what is noise. Here, noise in the sense, not the one what you are doing in the absence of teacher in your classrooms. Here, noise in the sense, not and definition, a sound which has no value is called as noise. Technical definition in general perspective. In general perspective, noise is a sound without any value, or else you can define it noise as an unwanted sound at an unwanted place at an unwanted timings is noise in a general perspective. But in a particular perspective of remote sensing, we are not supposed to call noise as the noise what you are thinking. What is the noise here? Here, noise in the sense, here in the de-stripping, the digital numbers are high and low, where entire line. Whereas in the removal of visual scan line, the line values are not scanned. That means in the first case, the numbers are not scanned. In the second case, the numbers are high and low values. Not at one particular point on the image, an entire line. This is called as systematic noise. The abnormalities in the entire line is systematic, but the abnormality at one particular point is called as noise. That means, see here, all these are the, all these are the digital numbers. If any number at any one particular point is very higher or very low, called as noise. That noise has to be removed. How you can remove? That's what here, random noise removal. See here, filter is, in the process of filtering, we can remove those random noise, random here and there. But in the de-stripping, entire line was missed in the first case. Here, at any one corner, at any one particular point, there is an abnormal digital number that has to be corrected. How you can correct it? Simply by the process of filtering. What is happening filtering here? Here a kernel, we can call it as a name, moving window. Simply applying a moving window on a digital image, we can remove those errors. See, let us have a look here. See here, The here when you compare here, the one is somewhat abnormal. It's look like, or else if you want to remove the value which is an abnormal, which is not synced with the neighboring pixels, is called as see the value which is not synced, which is not matched with the neighboring cell pixels, called as random noise. This random noise will be removed in the process of filtering. Filtering means the applying of 3 into 3 moving windows, 3 into 3 or 5 into 5, 1, 2, 3, 1, 2, 3, 3 into 3, on a place where which number you want to remove. Here, see here, filter is a simple sliding window spatial filter that replaces the center value in the window. See here, filter is a simple sliding window spatial filter that places the center value in the window with the average of all the pixel values. See here, 5 plus 3 plus 6 plus 2 plus 1 plus 9 plus 8 plus 4 plus 7 equal 45, and all these are 9 by 9, whatever the value got, that will be replaced to the center value. It is called as removal of random noise. What is noise here? The value which is not matched with the neighboring digital number values, which looks an abnormal, which looks an suppressive number, called as random noise. See here, the random noise has to be removed. How you can remove? Simply by the process of, or else by adopting the process of filtering. What is happening in the filtering? Simply see this 3 into 3 window where we are applying here. See, for suppose if you want to apply 3 into 3, see here, if you want to replace this 119 value, that replace the value will be as the window will be kept like this. See here, 170, 68, like this, 3 into 3. Then to this we are just adding 170 plus 136 plus 238 plus 68 plus 119 plus 255 plus 221 plus 17 plus 136. The answer x by 9 to replace the value of this 119. If it is in 5 into 5, like this, see here, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. See here, like this, 5 into 5 to replace the center value. See, if it is the small window kernel, so if you want to remove this value, we will go for 3 into 3 in the process by name removal of random noise, or else random noise removal. When we have a look here in radiometric correction, we have seen replacing missing scan line, de-stripping we have seen, random noise removal also we have seen. The next one is sun angle and topographic correction. How we can correct? Simply here, just to know the process, because of the solar radiation reflected diffusely on the ground surface, or a simple in one term, because of the diffusion of solar radiation, sometimes in the images there will be a light patches. Light patches are called as sunspots or solar spots. It can be removed by estimating a shading curve by using Fourier analysis. What is Fourier analysis? We are going to discuss in lab. The Fourier analysis, keep in mind, Fourier analysis is not in your syllabus point of view, and it is not any simple task to discuss. Okay, it takes many more classes. It is in a separate topic. That's why we are going to discuss in a laboratory Fourier analysis. See here, of course, with certain images, that is better easy to understand what is Fourier analysis than in this PPT mode. So see here, what I am speaking is here, by estimating a shading curve, the patches on the image, why those patches are observed on the image? Because of the diffusion of solar radiation on the ground surface. Sometimes there might be occurrence of small white patches, white spots on the image called as sunspots. They will be removed by estimating, okay, by estimating a shading curve, or else by estimating, see here, by estimating a shading curve with the help of Fourier analysis. Now here shading is another effect appears due to atmospheric shading curve there. See, this is what I am going to speaking is now. Sometimes shading, in the previous case, it is in a spot, hot spot, sunspot, the light patches. Here, sometimes the shading will be there on the images because of the topographic effects. Because of the topographic effects, a shading, some amount, see, the shading will be observed on image. That shading also will be removed with an angle that is determined. See, an angle corrected by using an angle between the radiation, between solar radiation direction and the position of vector to the ground surface. The previous case, the white patches are as hot, lighter areas which may occur because of the diffusion of solar radiation on the ground. On the images, there might be occurrence of light areas, and which we can remove by estimating a shading curve with Fourier analysis. In this case, there will be a shading. We may observe the shading because of the topographic effect, which can be removed by an angle, or is corrected by using an angle between the radiation, between the solar radiation, or as between the direction of solar radiation and the position of vector to the ground surface. That is called as sun angle topographic correction. Next is atmospheric correction. See here, in the first case, you have seen replacing missed scan line, we have seen de-stripping, we have seen random noise removal, we have seen sun angle and topographic correction, we have seen under what? Radiometric correction. Where this radiometric correction? In digital image processing. What are, there are two categories. One is radiometric correction, and another one is geometric correction. See here, the last one is atmospheric correction. How? Atmospheric, what are the, I mean, what are the consequences of this atmosphere? Simply, we discuss in the name of scattering, the atmospheric influence is because of the atmospheric constants like aerosols, water droplets, or water vapors, which makes the image and unclear, which reduces the resolution of image, and which are the reason for the improper image. Those images has to be removed before we are sending the data for processing. How can we remove those interferences? Simply, number of algorithms and procedures are there to remove the atmospheric flaws. The first one is ground truth data. Here, ground truth there itself, we are able to understand ground truth, that means seen evidences, we can call in another word. I have an image of one particular target which is unclear. By taking an image from the ground, or else by taking the resolution of ground data and comparing with this data what I'm having, I can remove the error, I can remove the flaw. What is ground truth data? I said that The comparison is in between the realistic ground truth data and the data what I got, then the information will be corrected. And the second one is using radiative transfer equation. See here, the radiative transfer equations for atmospheric correction of aerosol density in the NIR region and water vapor density in the thermal infrared zone should be estimated. The radiative transfer equations are developed. What is this radiative transfer equation? The radiative transfer equation is not in our in your lab, in your curriculum, but keep in mind, you must remember the word radiative transfer equations. What is this radiative transfer equations? What is this Fourier analysis that we are going to discuss, or are going to discuss in a more elaborate manner with visuals in laboratory? Simply by using radiative transfer equations, the density of aerosols in NIR region and water vapors in the aerosol region. When you make an attempt to remember about the scattering because of the atmospheric constituents which are due to the dust particles, aerosols, water vapors, gases like nitrogen, oxygen, all other constants. See other possible constants which shows its influence on which can influence the AMR. That means what I'm speaking is here the image is recording in electromagnetic spectrum. See here NIR region, near infrared. As you know, the spectrum has been divided into different spectral bands with respect to wavelength. We have seen UV band, X-rays, gamma rays, and near infrared zones, so on. We have seen the aerosol density and water vapor density at NIR region and thermal infrared zone can be understand or can be estimated by radiative transfer equations. If I estimated the density and the quantity, I can get the image. If I estimated the density, if I remove, I can get the actual image. And the next one is other methods. What is the other method here? A special sensor to measure aerosol density and water vapor density. In the previous case, by adopting radiative transfer equations, we are able to measure the density in NIR region and density of aerosols at NIR region and density of water vapor in the thermal infrared zone. Here, no need of applying radiative transfer equations. Simply, certain advanced satellites of NOAA we have seen there. NOAA, NASA, NOAA. See here, by applying certain NOAA satellites has not only an imaging sensor of advanced very high resolution radiometer, but also high resolution infraradiometer for correction of atmospheric flux. Example means the NOAA satellite is not only an imaging sensor of advanced very high resolution radiometer, but it can also remove the atmospheric flux in the bands. This is what about atmospheric correction. See, the electromagnetic radiation, while it is passing through the atmosphere, there is an influence, which means because of what the image's resolution will be influenced. To get back the original image, we are adopting, or simply we are using three methods. One is using ground truth data. You know, in your college, the exact where is the exact position of canteen. See, if you somebody is speaking against to the position what you know and what is exactly there, you can estimate. It is not. It is either it is right or not. Understand? See, your classes are, if you are, you know, your classes are in the first floor. If your classes are in the first floor, see, and you may not, if I mean, how you know, if the, I mean, if people are not there in the classroom, how you know? The moment, if you are not informed by anyone, simply by seeing the empty class, you can understand the class is shifted. Or as the class people are went to some other class. That means you are checking eyewitness ground truth data. See, I have a satellite image which is influenced by the atmospheric constituents where the resolution is not up to mark, where the image clarity is not up to mark. In such cases, the ground truth, the resolution of ground truth data is being compared with the spatial data. Then we can go for correction, that is ground truth data. And by applying radiative transfer equations, I can measure the density of aerosol in NIR region, and I can measure the density of water vapor at thermal infrared zone. If I measure the densities of those atmospheric constituents, I can get the image in those bands more clearly by using radiative transfer equations. Here in this case, certain advanced satellites may not need those equations. Simply, they have the removal of the capability of removing atmospheric corrections. Hope you know. See here, the technology is being upgraded. The compatibility, the missions will take the data on its convenient. Missions in the then softwares. For suppose, there are certain applications where where it will take automatic redirection if it is beyond the norms. For suppose, if you are sending a large file more than 25 MB through Gmail, a pop-up window will appear. More than 25 MB data will be sent to Google Drive, a link, you can share the link. If it is below 25 MB, the mail will be sent to the given address. What I'm speaking is here, there is no need of radiative transfer equations when these satellites are used. When the other satellites are used, you need to adopt the radiative transfer equations to remove the density at certain bands by name NIR and thermal infrared zones. Whereas when you are using advanced satellites like NOAA, which is very high advanced resolution radiometer, no need of equating any further equation. Simply, it has the feasibility of removing atmospheric flux. That is what about atmospheric correction. And the previous one we have seen sun angle. Sun angle in the sense removal of hot spot because of solar diffusion on ground surface. The image may hold sometimes, and light areas, those areas will be removed by estimating a shading curve with Fourier analysis. And the shading also may be observed to the images because of the topographic effects, and then that can be removed with an angle between the sun direction and the position of the vector or its object to the ground surface, vector object to the ground surface. See here, now the next one is random noise removal. The abnormal values at one particular point, not entire line, at one particular point is called as random. It's called as noise, as it is observing at the corners are here and there. We named it as random. And the removal, we can remove that random noise simply by adopting 3 into 3 window like this. Simply, we are summing all the values of the digital numbers by 9, and the value whatever we got that will be depicted in the part where we want to change the value. That is what about random noise removal. See, we have seen just now topographic correction. In here, in the first case, we have seen and shading curve is estimating. Here, a shading, I mean, an angle is, okay, an angle by using an angle between the radiation direction and the normal vector to the ground surface. An angle between the radiation direction and the normal vector to the ground surface can give the information how to overcome this shading effect on the images. And next one is de-stripping. De-stripping in the sense the high and low digital number values, entire line, those values will be removed by comparing with other standard satellite resolutions. That is one method, and the other one is by Fourier transformations, which can use in de-stripping. And we have seen how and why. See, these lines will mixed. How in the sense by adding the numbers of the digital numbers of previous line and subsequent line with average, we will depict the number here. How in the sense all these are happened due to the non-functioning of detectors. If two lines miss, the first line values are repeated with the previous line, and once we got the previous line values, by adding the previous line and subsequent line, the result is average by 2, the value will be in the second line. The value whatever we got, that will be depicted in the respective pixels of the line. This is what about removal of missing scan line. We have seen radiometric correction under digital image processing. If you have any doubts, you can contact me in the domain, whatever you feel comfort. Thank you.